Sage. A bit about me, I did my undergrad and master's degrees at MIT in ECS. I'm currently employed as a research scientist at Pasteur Labs. It's a startup doing AI for physics simulation. But tonight I'll be presenting some work I did during my master's in Philip Isola's lab. It's called neural refraction fields, not radiance fields, for image verification. So it's no secret by now that AI-powered image synthesis and deepfakes have exploded in the last few years. They are becoming increasingly advanced and accessible to the public. Generative AI allows for image splicing while maintaining coherence with the surrounding content. Deepfake tech has also been applied to video editing. So this is an Adobe, I think it was called like Project Morpheus, and they edited videos where they maintain like the temporal consistency across the frames and edit the person's face. I think most people here can tell that that looks pretty fake. That was from 2021, but fast forward to 2025, and so this is the top original video frames, and the bottom is, they gave it the text prompt to age the person. And this is pretty remarkable to me. Today, the results are often impossible to discern with just the human eye. So people are investigating how humans respond to this. We just saw an interesting presentation on that. And in this paper on the left, they showed that humans got something like 48% accuracy trying to distinguish real from style-again synthesized faces. So not so great, almost 50%. And same thing on the right. This is a more recent study from Microsoft's AI for Good lab, where they gave you this quiz called Real or Not. You just answer whether something's AI or real. The quiz basically has like 15 images sampled from a much larger set. And the humans also did not do too well on that, pretty close to 50% in all categories. Not to brag, but I took the quiz for fun myself, and I'm in the 92nd percentile. So that verifies a hypothesis of my own. Maybe ChatGPT might lower you by, 15.3%? But as an avid student of manipulated images, I've been staring at them for so many months. I think humans are capable of training themselves to recognize AI content, at least maybe for the next year. In fact, when asked on tips for recognizing AI-generated media, a leading expert in the field, Hani Farid, said, whatever I tell you today is not going to help you a month from now. Ironically, he said that about a month ago, so we might not trust that. So separate from investigating like human discernment capabilities, image forensics is this field now that has emerged to combat the risks computationally. Image verification is a subset of that field that involves verifying whether an image is authentic or synthetic, or just manipulated in some synthetic way. There's different approaches to image verification. So broadly speaking, there's like two large buckets. On the left, you have more like physics-based analyses where you look for physical artifacts. And on the right, you have more data-driven analyses where you look for artifacts in the data. So, for example, the paper on the left is a paper from Farid also, and they're just using different physical laws from like photography, optics, perspective, projection, to show that there are geometric inconsistencies in, this was DALL-E paint by text synthesized images, which of course don't explicitly model these geometric principles in their models, also because the human visual system is often oblivious to these geometric inconsistencies. So they explored how fruitful this type of analysis would be in detecting this new breed of synthetic media. So they're using concepts like from like classical computer vision, vanishing points and vanishing lines, and finding all sorts of inconsistencies that are not obvious to us. But on the other hand, and a much more popular approach is to find artifacts left in representations of the data. So for example, you can test whether you can discriminate real from fake images by looking at the underlying data distributions. Here on this paper used lower dimensional, learn linear embeddings using PCA. And the blue is using StyleGAN, the red is real profile photos, and they found that the reconstructions off of those learned embeddings had very different distributions of error. So, and also, these are all called passive approaches to image verification, as in you're investigating things after the fact, but you can also do an active approach, which is before the fact, like watermarking. So we're still leaving everything in the hands of the software. And what can the subject of the photo actually do to protect themselves? After all, they have no control over the person taking the photo or the post-processing. They can only control things in the physical world with them. They can only interface with the software via the photons that bounce off their body. So what if we physically placed this decorative glass object in the scene? Maybe it can act as a sort of physical watermark, and you could tell if recordings of the room are real or fake if we look closely at it and maybe check to see if all the refractions are right. So if some adversary comes along and edits the image, how can we tell whether it's trustworthy? Well, we can take a look at the vase, and from the warped, scrambled data in it, we can find geometric inconsistencies in the refraction and determine that the speaker was never holding a flag during the photography. So this framework for watermarking images in a physically constrained way was introduced in prior work called totems. The idea is that you digitally sign an image by placing 4 glass spheres called totems in the scene, inspired by the movie Inception. And it watermarks it in a natural way and directly embedded in the physical setup. So these totems provide multiple warped views of the scene. And with multiple views of the scene, you can train a NeRF to reconstruct the original scene in 3D. So that's exactly what they do. By bending the light rays through the totem and according to the known refractive laws, you can get some sort of NeRF reconstructed view and compare it to the unverified image to detect anomalies. So just to walk through this example over here, a person wants to protect an image. They place these 4 glass spheres at the front of it. Somebody splices in another person in the image, and then we get a NeRF reconstructed view, and then we can detect this person is fake and some sort of inconsistency heat map. So this was a really unique and novel approach because it marked one of the first attempts at combining learning-based and physically based, optics-based techniques together. And it's also an active approach and allows somebody to protect themselves directly in the physical setting. But it does have a few limitations. One being the practical inconvenience of requiring 4 large totems to be placed in the scene, which is driven by the need for multi-view depth correspondence. And even 2 totems might not be enough to achieve convergence. And second, the reliance on per-scene retraining hinders the applicability to dynamic environments like video. It's pretty inconvenient. And the biggest limitation, though, is that the requirement for a closed-form refraction of how the light rays get bent in order to shoot them into the volume to optimize the NeRF. And that depends on all sorts of things like the totem geometry and the material properties, and that's highly inconvenient. I also want to mention very quickly that the key, the cryptographic framing of this and the reason why it's considered secure is because they assume that an adversary cannot make geometrically consistent manipulations both in the image and in the 4 totems. So the totems informally act as private keys where their index of refraction, their geometries are only known to the defender. So they're these sources of truth that allow you to detect inconsistencies. But in reality, a sphere is not really so secure. I think you can sort of pass the detector with that. So we introduced a new framework for refraction-based image verification that overcomes these limitations. And it's based on the key idea that rather than using a closed form model of the physics, we instead learn a model of the refraction, which we call a neural refraction field. And from that, we can just build 2D reconstructions, and we only need one totem in the scene. We can learn the model independent of the RGB values in the scene, and we can hopefully generalize to shapes beyond a sphere. So we do this by, we train this model using synthetic training data that's empirically generated, which I'll walk through now. So to recap, a totem is just this like signal that's embedded in the image I, and it creates some transformation I prime. And the way we synthesize data is by scanning a laser over the depth map of the scene. And at every sample point of the image, we record the corresponding refraction found in the totem. So to demonstrate our approach, we're doing everything in simulation. So we make a few approximations, like assuming the scene is infinitely far away. So we represent it with a flat image. In the future, we hope to relax this. And we continue this process of like scanning the laser and collecting coordinate correspondences between scene and totem, or image and totem pixels. And we build out some sort of data set. This is like the full color correspondence. But this is a bit slow. And in the real world, it's not feasible for a human to scan with 100% coverage. So here we tested this out in the real world, and the human is moving a laser against the wall. That's the red crosshair, and this is our algorithm, the blue crosshair, detecting where the refraction is being found. And so it's a pretty sparse coverage. So we try to do that as well. What we can do is conduct the sweep in software at some reduced granularity, and then train a model to learn the mapping and interpolate the missing points. So when an unverified image comes along, this one has been edited, what we can do is use the correspondences to reconstruct an estimate of the image based only on the pixels in the totem. So it's basically just unscrambling the transformed signal. And then we can compare these two versions to detect inconsistencies, and then evaluate it with some average precision score. So just to go over the model implementation, again, the goal of the model is to estimate the inverse of the totem transformation. The reason why we want to learn the reverse mapping and not the forward mapping is because it is from scene to totem pixels, it's a many-to-one function, just by nature of the finite resolution, the totem being smaller. And to avoid the complexities of multi-output models, we'd rather learn the reverse function. So this is a smooth many-to-one function. And in line with previous work, we found that using just a simple 8-layer MLP is enough to represent these refractions. And we call it a refraction field, neural field with refractions to represent how the pixels get transformed. So we use like 7 layers, ReLU activation, the skip connection, mean squared error between the predicted and target coordinates. And here are some sample reconstruction results over the course of model training using like frozen weights. Something interesting is that in this area that's occluded by the totem, there's no training data, and it still does quite a good job at interpolating in that region. This is the ground truth. And here are some detection results we get for image splices. So to make detections, we compute the patchwise absolute difference between the reconstruction and the unverified image, sort of as a predicted manipulation map of probability estimates. And then to evaluate, we calculate the average precision score against some ground truth. So here, blue means less detection, red means more detection. Here's another example where we're comparing to the prior work. So this image over here is the totem's original setup. We have to crop it just to get rid of the totems and add our own in simulation. And then we test out a color patch manipulation. And so here's the totem's result. Here's our result. it still does pretty well, but the main issue is that there's so much reconstruction error that the detection is less pixel precise, whereas ours is more precise to the exact pixels in the color patch. Now, obviously, a sphere is not very secure, and zooming back out to the idea that a totem just embeds some lossy nonlinear transformation of the image pixels, what if we considered more general transformations, maybe something a little less smooth? So by enabling independence of a closed form of the refraction, we open the door to potentially more secure totem geometries. However, there's a few challenges, one being, it's a little hard to see here, but there's like additional red clusters of pixels along the teapot due to higher order and internal reflections and refractions. And so the question becomes, how can we keep this many to oneness in our model and choose the most prominent cluster of pixels that will be the least noisy? So we use a few heuristics, such as selecting like the largest cluster, grouping things together, selectively tuning the laser size, the laser frequency in the real world, the detection threshold. So that's just a small point of there was a slight challenge with that. But also another challenge is that these shapes are harder to model because of their non-smooth mapping function. So take a really complex shape like the toroid knot, and because it has such a high frequency mapping function, our current model can't capture this pattern. But we found that by introducing positional embedding, we can get some pretty promising initial results. This is an ablation study without and with positional embedding. We also tested the number of frequencies, and we found that 10 was usually like a happy medium between overfitting and loss of representational power. So this is really cool, I think, that it sort of allows us to the model becomes sort of like a Fourier feature network where it can represent the different frequencies in the mapping function. Here are a few other results. It definitely doesn't do great behind the totem. Not that that's so important for image verification. And there's definitely future work to be done in general. But here is a detection result. Here, so this compares, here I'm just showing the reconstruction. This is the toroid knot. This was the sphere for reference. And down here we have the sphere versus the knot detection results. And so we're starting to see this trade-off between more secure shapes but less precise detections, at least with the current state of the model. So right now it's probably best suited for larger regional manipulations, but maybe switching the loss metric, like how we're detecting differences between the two images. Right now we're just using an absolute loss, but one thought was using LPIPs could help emphasize perceptual differences better and be more robust to reconstruction error. So to recap, an active image verification pipeline that embeds this signature based on physical refraction. It's a really niche topic, I think, but it was a really interesting exploration of how we can model these transformations from in glass objects, or maybe in the future in other materials. My PI had a vision that one day celebrities might wear like totem necklaces, and that could protect them. And there's definitely future work to be done on improving the accuracy of the reconstructions. But and also our method is directly translatable to the real world. So I'll end by showing an initial result in the real world. This was in that same gray wall. And there's definitely some noise over here. That was due to the fact that it was like really bright here and the laser was getting really faint. So we needed to use like a stronger laser. I think we were using a green one here. And there were other sorts of non-idealities that we didn't have to deal with in simulation. But yeah, thank you so much. And I don't have a QR code, but if anyone has any questions, and I'm also on LinkedIn, so we can connect there.